Development of microchips, or integrated circuits, ICs, can be traced back to the mid-20th century. The invention of the microchip is commonly attributed to Jack Kilby and Robert Noyce, who independently developed the concept around the same time. Jack Kilby, 1958. Jack Kilby, working at Texas Instruments, is credited with creating the first integrated circuit in 1958. Kilby's approach involved fabricating all the components, transistors, resistors, capacitors, on a single piece of semiconductor material, germanium in this case. He demonstrated a working prototype showing that multiple electronic components could be integrated onto a single chip of semiconductor material. Robert Noyce, 1959. Robert Noyce, working at Fairchild Semiconductor, independently developed the idea of the integrated circuit in 1959. Noyce's approach was slightly different from Kilby's. He used a planar process, which involved creating the components on a flat surface, making it easier to mass-produce integrated circuits. Both Kilby and Noyce's contributions were crucial to the development of microchips, and interestingly, both received credit for the invention. Kilby was awarded the Nobel Prize in Physics in 2000 for his part in the invention of the integrated circuit. The early microchips were relatively simple and had a limited number of components compared to the highly complex chips we have today. Over the years, advancements in semiconductor technology have led to the development of smaller, more powerful, and more energy-efficient microchips. Evolution of microchip manufacturing, small-scale integration, SSI. This phase involved integrating a small number of transistors, tens of transistors, on a single chip. Medium-scale integration, MSI. The number of components on a chip increased to a few hundred, allowing for more complex functions. Large-scale integration, LSI. LSI chips contained thousands of transistors, enabling the creation of more sophisticated electronic devices. Very large-scale integration, VLSI. The number of components continued to increase, reaching into the teens or hundreds of thousands of transistors per chip. Ultra-large-scale integration, ULSI, and beyond. With the advent of ULSI, chips now contain millions or even billions of transistors. This level of integration has enabled the development of powerful computers, smartphones, and a wide range of electronic devices. The process of making microchips has evolved as well, with advances in lithography, materials science, and semiconductor manufacturing techniques. Today, semiconductor fabrication facilities, fabs, use highly automated and controlled processes to produce intricate microchips on large silicon wafers, as described in the previous response. Hello dear, is you're new? Please make sure you subscribe and watch till the end. Also don't forget to comment, like and share. Thanks. Creating microchips is a process that transforms the seemingly simple substance of sand into incredibly complex devices containing millions of components. Despite the use of sophisticated technology, it takes a considerable 12 hours to manufacture a single microchip in multi-billion-dollar fabrication plants known as fabs. These plants primarily use silicon, a semiconductor that, under specific conditions, can conduct or insulate electricity, making it ideal for electronic applications. Hello guys, welcome to Global Crafters. 1. The best factory discussing channel. Please show your support by hitting the subscribe button, like, and share your opinion in the comments section. Thanks. Let's get back to the video. Silicon's abundance in nature and its ability to meet the diverse needs of electronic devices make it a cost-effective choice for microchip production. However, most naturally occurring, silicon is chemically bound to oxygen, requiring a separation process. Sand, a readily available source of silicon, undergoes a transformation by combining with carbon dioxide and melting in crucibles. This process results in 99.9% pure silicon, which is further refined to achieve ultra-pure silicon. The production process then involves the use of seed crystals placed in contact with molten silicon, resulting in the formation of a single crystal of pure silicon. This crystal is then sliced into thin wafers using a wafer slicer. These wafers, on which integrated circuits will be formed, undergo polishing to eliminate impurities. The entire process takes place in a clean room environment where air is filtered to remove foreign particles, and operators wear specialized garments to prevent contamination. To create the microchip's foundation, a layer of silicon dioxide is applied to the wafer surface to act as an insulating base and prevent oxidation. The next step involves designing the circuit on a computer-aided drafting machine, which is then converted into a mask. These masks, acting as stencils, define the patterns and structures transferred onto the silicon wafer during the photolithography process. In photolithography, a photoresist material is applied to the wafer, exposed to ultraviolet light through the mask, and then chemically processed. This critical step embeds the circuitry pattern onto the wafer. The wafer then undergoes chemical etching to remove unexposed areas, creating the three-dimensional microchip. To achieve the desired electrical properties, specific areas of the silicon are doped with impurities through processes like diffusion or ion implantation. Various materials, including metals and insulators, are deposited onto the wafer's surface to create conductive paths and insulating layers. The fabrication process involves multiple lithography and etching steps to build up layers of circuits, adding complexity to the chip's design. Microchips typically consist of fundamental components such as capacitors, resistors, and transistors. The number of transistors on a chip can be extensive, exceeding 28 billion in advanced chips found in high-end graphics cards, contributing to enhanced computational power. After fabrication, the wafer undergoes testing to identify and eliminate defective chips, ensuring quality control. Verified chips are then separated, placed into protective packages, providing electrical connections, and subjected to final testing to meet specified performance criteria. While the rejection rate of chips has decreased over the years, the intricate process of creating a microscopic lattice of circuits and components remains challenging. Looking to the future, advancements may involve entirely new circuit technologies, possibly transitioning from mineral-based to biological components. Despite the complexities, understanding the microchip manufacturing process sheds light on the remarkable evolution of electronic devices. So tell me if you enjoy this video and what did you learn here. Also, don't forget to subscribe, because we will be dropping another video soon. Hello guys, welcome to Global Crafters 1, the best factory discussing channel. Please show your support by hitting the subscribe button, like, and share your opinion in the comments section. Thanks. Let's get back to the video. Silicon's abundance in nature and its ability to meet the diverse needs of electronic devices make it a cost-effective choice for microchips.